In this video, we'll take the idea of matrices and tie those back into the idea of solving systems of equations. So linear algebra and this idea of matrices sort of gets built out of trying to systematically analyze solving systems of equations. So an example of this, or system equation we might try to solve, is something like this. This here's two components, so easy to have to work out by hand, but you could imagine a system equation that involves a lot more components than this. Now, how do we go about solving the system here? Well, the sort of main method that you probably already learned is elimination, right? I want to eliminate one variable from the entire equation by combining the equations together in some sort of way to then get an easier equation to solve that just has one variable in it. So for elimination, what I'm going to do, for this case here, I would basically multiply the second equation by 3, then add the equations together. If I do that, I'll result in 5x1 equals 5, which easily tells me that x1 is 1. And I can solve for x2 by plugging back into either equation to get that x2 is also 1. So my solution here is 1, 1. Great, we found it. But that worked nicely for having two equations. If I have more equations, I want a more systematic approach to how I can always do this process and always step forward one step at a time to get to an answer. So let's step back for a second and think about what kind of operations can we perform with these equations that make sense and can move us towards answers via elimination. So what can we do? Well, one thing we can do, which might seem odd and not really useful, is we can swap the order of two equations. This doesn't really help us move towards a solution, but it might help us visualize what's going on. Right? If I had a whole bunch more going on here, I wanted to put this equation, these two equations next to each other so I could see how to solve them out. That's why swapping the order might help me visualize what's happening here. So option 2 is I can multiply any equation, the entire thing, by a number, which would do multiply by 3 the entire equation there. Now the third thing I can do is I can add some multiple of one equation to another. Here we just added the two equations together, so one multiple of one equation to one multiple of another, that's fine. We could have also done this in one step, just adding 3 times equation 2 to equation 1 to cancel things out. Right, but those are the 3 main steps in this process. We can phrase anything we do with elimination in terms of these 3 steps. And our goal is going to be to take this process and figure out a systematic way of implementing it that it will always work to always get us the answer we want for these kinds of problems. But to do that, I want to take a step back from these equations and sort of abstract away some of the information we don't actually need when trying to solve this problem. And that comes to the idea of matrix vector multiplication. So if I take the system equations here, a different one than we had before, and I combine them into sort of a vector stacked equation, what I'm really saying here is that the vector 3x1 plus 4x2 on top, x1 minus 5x2 on the bottom equals the vector 6, 1. So as a vector, things are equal if all the components are equal, so I can write it this way. But then this here looks like dot products, and so I can rewrite that side as matrix vector multiplication, multiplying the matrix 3, 4, 1, minus 5 by the vector x1, x2 to get 6, 1. So this here is the matrix form of that system of equations. Now if we look at this, the x1, x2 here really isn't important. All the information about this problem is characterized by the matrix on the left and the vector on the right side. So I can kind of ignore the x1, x2. It's not really important when I'm trying to solve out this problem. However, I need both the left and right hand side to handle this problem. And so I want to sort of remove the x1, x2 and get to a new form that I'm going to use to solve this problem. And that gives us the idea of what's called an augmented matrix. For the problem here, it's the matrix 3, 4, 1, minus 5, and then you tack on to the right side the 6 and 1 from the right side of the equation. You can put that dash line in there to separate them, or you can leave it off. Either way is fine. It's nice to have it there to sort of show how it comes from the equations in the first place. So this augmented matrix here, you also see this written in the form A for the big matrix, and then B for the vector on the right-hand side, contains all the information from this problem. It is, in a sense, a system of equations where I've sort of gotten rid of the letters that correspond to the variables and just think about them in general as how they behave as a system of equations. Our goal is going to be to figure out how can we take this augmented matrix and make it into a form that's easy to read off solutions. What do we mean by that? Well, what would be an easy matrix, an easy augmented matrix from which we can read off the solutions? Well, if I have something that looks like this, what does that correspond to in terms of system of equations? Well, if I do the whole process backwards, this is 1, 0, 0, 1 times x1, x2 equals 2, 3. Or writing that out, x1 equals 2, x2 equals 3. So if I had my matrix in this kind of a form instead, I can just read off, this tells me that x1, that's in the first column, equals 2, and x2, that's in the second column, equals 3. I'm done, there's my answer. So our goal is going to come up with a process to turn any augmented matrix, any form like this, into one where I can just read off the answers from the matrix. It turns out this process has other uses in sort of concepts of linear algebra, but the main way we use it here is to work from an arbitrary system of equations and get to something where the solution's right there in front of us. We can read off the answer and know what the solution is to that system. And this process that's coming soon is called row reduction. So that's the idea of how we can take a system of equations, write it in an augmented matrix form, and then hopefully be able to use that form to get us towards working towards a solution of the system of equations.